Hello everyone, I'm Midas Lambrichts and I'm here today to talk to you about Fuzz-driven development, when you know and you don't know. So, first of all, who am I? As I said, I'm Midas Lambrichts, and by day I'm a senior software engineer for the refueling solutions, and by night I'm a Rust enthusiast. I also have various social media on which you can find me. I'm not the most active person, but if you have any questions or just want to chat, you can reach me on these. For the people attending RustConf, you can also reach me right now in the Discord if you have any questions or if anything is unclear. So for the subtitle, when you know and you don't know, this refers to one of the strengths of Fuzz-driven development, that even with a minimal amount of domain knowledge, you'll still write decent software without any major mistakes, because Fuzz-driven development will guide you through it and you'll learn as you go without having to fear that you've just made a big whoopsie. You only need to be able to come up with one simple thing, some invariant, and the rest you'll learn as you go. But to understand Fuzz-driven development, we first of course have to understand what fuzzing is. So fuzzing, according to the Rust Fuzz book, which is an excellent resource for anyone getting started with fuzzing, fuzz testing is a software testing technique used to find security and stability issues by providing pseudo-random data as input to the software. So basically what it's going to do, it's just going to come up with random data and give that as input to your software. And then it's going to monitor your software for some things. Most of the time it's going to just see if your software crashes. If it crashes, it'll report that back to you that for this input, something crashed. There are other variants. Sometimes it will keep fuzzing indefinitely and just collect crashes, and then when you say, okay, you can stop running, it'll report them all in one go. If that's not clear yet, we'll see also a bit of fuzzing later on once we go through an example, and that should clarify it for you. Okay, so we have fuzzing, now fuzz-driven development. So fuzz-driven development is a 6-step process, of which the first one is determine an invariant. So that was a C that I was referring to earlier, the one thing that you need to know. This doesn't always need to be correct. You can start with an incorrect invariant. You just need to be able to come up with a starting point. Second step, you provide a fuzz target that expresses that invariant for you. Fuzzing target sits between the fuzzer and your software, which can do a bit of manipulation on the data before passing it along to your software. Then we're going to run the fuzzer until it gives us a failure. And we're going to think about, why did this fail our software? Why does this cause a crash or whatever? And then depending on our reflection, we might just have to write some new unit tests and do some development. And then step 6, the final step, is a non-final step because it's iteration. You're going to restart again. Most of the time, certainly with more mature projects or when you've been doing fuzz-driven development for a while, most of the time you're just going to return to step 3, run your fuzzer again until it finds another failure, another bug in your program. Sometimes you also notice that this doesn't really make sense if you reflect on it, and that might be because your fuzzing target doesn't really express the invariant that you want. So you might have to change your fuzzing target. Sometimes you'll even, after the reflection, see that your invariant actually doesn't make sense or isn't very good. So you have to change the invariant. So these are the 6 steps of fuzz-driven development. Now, let's try to map this on where where in the wild you'll find most fuzzers today, or fuzzing targets today, and that's on parsers or compilers. So the first one is determining an invariant. For a parser, most of the time this is going to be, it shouldn't panic. It should either return an error or an okay, but it should not panic. Also goes for most compilers. It should accept or reject, but it shouldn't crash. Then a fuzzing target that expresses this invariant, you just take whatever input the fuzzer comes up with and you pass that along to your parser. You don't even care about, okay, our error just doesn't crash. Then we're gonna run the fuzzer until it fails, which in this case means that our parser crashed somewhere, that it panicked somewhere. And we're gonna think about why. Most of the time this is just some path you missed or something like that. But since we have a pretty simple fuzzing target and a pretty simple invariant, it's very unlikely that it's gonna be one of those two. So you're gonna write a unit test for this input, which just gives this input, so that your test coverage increases, and then you develop such that the test passes. And you iterate again, in this case most of the time, back to step 3. So now that we know fuzz-driven development, or have seen it for a bit, we're gonna write a library which by using fuzz-driven development to develop it. The library that we're gonna write is a JSON Patch squasher. Most of you will know what JSON is, but what is a JSON Patch? So assume we have this JSON document to start with. 2 properties, a name with the value mids and a ranking 8. Later on, the user gains some popularity, his ranking goes up, he goes to rank 5. Okay, he gains some more popularity, a bit more, his ranking goes up to 4. These changes, we can express them as a JSON document itself. So the change from ranking 5 to 4, we can say, and as a JSON array, there's an operation there to replace /ranking, so that property from the root, with value 4. Again, if the user, for example, changes his name, and by consequence his ranking drops a lot, there's another JSON patch for that change, one to change the ranking to 950 and one to change the name. Those are 2 patch operations, and this is one JSON patch. That array is the JSON patch. The entries in it are the patch operations. So then again, another change, the ranking shoots up to 1, he did something amazing. Another JSON patch, an array with 1 operation in it to change the ranking to the value 1. So those are JSON patches. Now we know what JSON patches are. Now the squashing part. So if we have our operations from before, our JSON patches, we can express the same effect from that starting document to get to the same end document shorter. So in this case, we can express the same thing from the same starting document to get to the same end document by just replacing the ranking with 1 and the name with Midas. And that has the same effect scoped out on these documents, on the starting document. And that's the squashing operation that we're going to try to do. So now we know what we're trying to write. Okay, that's what our library is going to do. It's going to take this squashing. It takes a set of patches and it tries to minimize it a bit. So the library is going to look like this. We have a public function which takes the patches, and that's going to forward basically to squash operations, which takes an iterator over all the operations and all of the patches. And for now, we're just going to leave to do in there, so we don't have any logic yet. And this is our starting point now. So this is what we're going to use for fuzz-driven development. So step 1, we're going to write an invariant. We're going to come up with an invariant. And then this is what I said before. The effect should be the same. So the effect of applying the squashed patch should be the same as applying all the patches that were squashed in their order. That's the invariant. This is then if we do this, it's still correct. It's still, the squashed is still doing the same thing. So step 2, the fuzzing target. This is what it looks like for cargo fuzz. Fuzz target, exclamation mark. Then the data is what the fuzzer is giving you. So we take what the fuzzer gives us, the data, and then we're going to see if it matches an input struct, if we can deserialize it into our input struct. If it can, okay, great, we'll return that and we'll return that, assign it to the input variable. If it doesn't, then we return from this function, from this closure, such that the fuzzer itself will mutate again and try the next iteration, because we can't make sense of what it has given us. The input struct itself is two things. One, starting value, so we can apply patches to it to see if our squashed patch does the same, and then the patches themselves. So if we have that, then we're gonna squash the patches from the input. That's what our library is gonna do. And then we're gonna apply the patches in order that we've been given them, that the fuzzer has generated for us, to get our normal result. And then we're gonna apply our patch to the starting value to get the squashed result. And then we're gonna see if they're the same. They should, because it's the same effect, the end documents should be the same. So this is our fuzzing target in this case. So, step 3, running until failure. If nobody has ever seen it, this is what it looks like when you start a fuzzer. I sped it up with a factor of 100 because this took a while. But I'd like to draw your attention again to that we still don't have any implementation. We still have to do in there. And by showing this, I'd like to show that fuzzing can only show the presence of bugs and it can't show the absence. So it can come up with counterexamples of where we fail to uphold our invariant, but it can't guarantee us that we're upholding the invariant. And what I'm trying to show here is that duration of the fuzzing before it fails does not equal quality, sorry. Because again, we still have that to do in there. So, step 4, reflect. Well, it took a while to get our first crash, so it's difficult for the fuzzer to come up with the input struct that we expect. There are some other ways around this. There's structure-aware fuzzing. You can read about it in the Fuzz book, RustFuzz book. You can seed the fuzzer with some data, but that's outside of the scope of this talk. And then this is for brevity. Normally this would become obvious after a few iterations, but I'm gonna already do it here, is that the start state and the patches don't always make sense together. For example, after a while you might come up with something, the fuzzer might give you something like this, that you have a name and a ranking, and then it's the operation, the patch is remove a non-existing property. If we do this in our fuzzing target, it would fail because we cannot apply the patch to the document. So it's not gonna fail because we do something wrong or our library can be 100% correct, but purely the patch doesn't make sense on the document. So that's what we reflected about. This is a bit of a shortcut to get you to come along with the next steps because they are a bit more important now. So we're gonna iterate. So we saw that, yeah, we have some problems with our fuzzing target, but it could also be that our invariant isn't that great. So let's take another look at our invariant. So what we had was the effect of applying the squashed patch should be the same as applying all the patches that were squashed in their order. This doesn't express anything about what we're actually trying to do, the squashing. I basically can return one patch that's all the other patches together, and that would still have this invariant. If we can come up with an invariant that also expresses, besides the effect that it should minimize it, then we'll have a better progression through our fuzz-driven development. So as a keen-eyed among you might have noticed earlier on the example, is that if you take the initial document and the end document and you calculate the patch between those, that you have the minimal diff that we can squash towards. If we have all the other ones, the beginning and the end, that's the minimal one. You can't do a shorter expression of the difference between start and end than the difference between start and end. So that's our goal, that's what we're trying to achieve. So that's what we're going to compare against. We're no longer looking at the effect, but we're looking at the patch itself. So to pour this into a fuzzing target, step 2, we no longer try to deserialize into the input script. Now we're deserializing into a vector of consequent JSON values, such that we ourselves can calculate consequent patches between them. So again, if we can do this, we continue. If we can't, we return. Fuzzer will mutate again because we don't crash, and gives us a next input that might be deserializable. Also, again, because we're gonna calculate patches, if we only get 1 or 0 document, we can't calculate subsequent patches, so we're not gonna be able to do anything with that. Same story, just return such that Fuzzer will mutate again. Then we're gonna do that actual calculation to get all the patches between all the documents. And we're also gonna calculate what I'm calling the global patch, the one between the first one and the last one, because that's the one that's minimal, that's the one that we're gonna compare against. And then we're gonna squash the patches and then compare. There's a bit more boilerplate here because our library, if you have 0 patch operations, it will return none instead of a patch with 0 operations. So that's a bit more boilerplate, but it's just comparing the minimal diff with what we squash into. So now we're gonna run until failure, and then after a while, this is what we're gonna be greeted with, that the thread unnamed panicked not yet implemented, because still we have that to do in there. And then we're also shown what input caused the failure. And if we zoom in on that a bit, we can see that it's 2, 1, an array of 2 and 1, new line, tab, new line. But for us, only this is important, an array of 2 and 1. So first document is 2, the second document is 1, and that the fuzzing target will calculate a patch between them and give that patch, because there's only 2 documents, so 1 patch, give the patch to our library, and then we'll hit to do. So let's reflect a bit. Might actually help to write something that does something instead of leaving to do. So an actual implementation might help. So we're gonna take whatever the failing input was, in this case an array of 2 and 1. And what I like to do is write an helper function that basically does the same as a fuzzing target, such that I can write these very neat, very tiny unit tests very quickly by just copy-pasting that input from the fuzzer into here. So this is our first unit test. Our logic now is just to do, and the minimal thing that we can do to make this pass is just return all of the patch operations as a vector, and that would then result in the unit test succeeding, and we can iterate again. So we again run until failure. This time we have a bit of a bigger error message at the end, but the important parts are the assertion failed message, so the left versus the right, with the global patch versus the squashed patch. And at the bottom again we have the input that failed. So now we have 3 consequent documents of a number 44, a number 4, and a number 7. And then if I tidy this up a bit to make it a bit more readable, the global patch would be replace the root with number 7. What our library right now returns is replace the root with 4 and then replace the root with 7. So let's think about this a bit. So I see that if the path is the same, that I only need to care about the last one. And we still have 2 operations, but the first one has the same path, and it's the second one that basically still has an effect at the end. So when multiple operations are there for the same path, We only need to keep the last one. So we again port this into a unit test. Again, same thing, only the input needs to change this for this, and another name, of course. And then we develop. So our implementation, instead of just collecting into the vector, now we're gonna use a hash map from the path to the patch operation. Loop to all operations and insert them by their path. And yeah, if you insert something that already exists, then it is going to be overwritten in the hash map. So then to get back into our vector of patch operations, we just drain the hash map and only care about the patch operation. The paths that we use as keys, we can drop them. We only need the patch operations as a vector, so we collect it again. So this will make our unit test pass again. So we can iterate again. We can run it until failure. This time, this is what we'll end up with. The failing input would be 4, an array with 2 inside it, and an empty array. The global patch here will be replace the root by an empty array. Wheel or squash operations will still return replace the root with an array with number 2 inside of it, and then remove the first element of the root. So here we see that our previous assumption still holds, that the same path needs to be squashed, because this one is talking about a different path. So for a different path, we still might have to squash. So that's our reflection. Even if the path is different, we might still have to do some squashing between them. So we'll write a unit test again, and then we develop. This is way too much code to show you, but the main idea is you use a radix tree, which can give you keys, so the paths which are parents or prefixes of the path you're currently looking at, or all the keys which start with the prefix that you give it, so basically children potentially of what you're using. And then you have all sorts of combinations you can get into. I'm not going to show it here for brevity's sake. But after you've done that and the unit test passes, we're going to iterate again. I know, fun times. So we're going to run it until failure. This time our failing input looks something like this. An empty object, 0, an empty object. The global patch is going to be empty because you're going to compare an empty object with an empty object. You don't need to do anything. Our library will return that the squashed patch is a replace operation with the root path and replace it with an empty object. So our previous assumptions still hold. This is all operating on the root path. But if you think a bit about this, and more in terms of the patches, is that the patches don't contain any information where you come from. If this initial document, this empty object, was anything else, we would succeed. And then the patch operation would be, the squashed patch and the global patch would be the same again. But yeah, the JSON patches don't contain any information from where you started. It only describes where you go to. Like you start from something and you replace it with, and then that value is contained in the patch. What value you started with is not contained in the patch. So here actually we can realize that the patches themselves don't contain enough information to always come up with a minimal patch, because we don't know what you start from. So that's our reflection this time again. Sometimes it's impossible to get that minimal diff solely from the patches. You'll need the starting document as well to be able to come up with that, that minimal diff, the minimal patch. So we have two options now. We can either change our libraries API so you'll have to pass in that starting document as well, and that way we can guarantee that we'll be able to calculate the minimal diff, or we can allow for suboptimal results if you find it more important that you don't have to give in the initial document. Based on what you want to do, you're going to develop some more unit tests or not, and you're going to iterate, because if you choose one of those options, you'll have to come up with a new invariant, because for the second one, the allowing suboptimal results breaks our invariant, so we'll have to come up with another one or do some conditions on our invariant. So what we've been doing, again, the 6 steps of fuzz-driven development: you determine an invariant, you write a fuzzing target that expresses an invariant, you run it until failure, you reflect on that failure, potentially develop and do some unit testing, and then you iterate again. Those are the 6 steps of fuzz-driven development. So why does this work? Well, why this works is because what we're doing on a broader scope than the 6 steps. So what we're doing is basically we are using a non-cognitive process, fuzzing, so the Fuzzer software, which is a program, that to drive and guide our cognitive development of software. And we just need to provide a simple seed and invariant. So we start with a little bit of cognitive work, and now we let the Fuzzer guide us and show us where we're lacking in our invariant implementation, expression of our invariant. So why this is good, or why you might want to use it, is because the cognitive gaps that you might have, if you have limited domain knowledge, they get less chance to manifest, because you're not driving what you're going to implement next. Is the Fuzzer that's going to show you here there's still something missing and you need to take care of it. So for example, you might not have, or I didn't think about the different paths still having to be combined together for a minimal patch, or that you might have to provide the starting document to be able to give that minimal patch in some cases. Those are things that are important to know if you want to write a good library, but I didn't know those, and I'm not sure if any of you already saw those or could think of those. So with a very limited domain knowledge, we've still written a library which already does a lot, and we don't have to be afraid that we've embedded some of our lack of knowledge in there, which will come back to bite us in the ass later on. So with that, I hope that I've given you a new tool to put in your developer arsenal, which is fuzz-driven development, and I hope you have fun at the rest of the conference. And if you still have questions, I'm still in Discord, so maybe talk to you there. Bye everyone.